share. Okay, let me go to. Okay, I hope you guys tried the assignment earnestly. And I know Arena had a question last week. Why am I showing that? Because this is really part one of the problem that you have on the exam. In other words, the first part is design the exterior wall. And then after that, once the exterior wall is designed, we're going to learn today how to design the lintels and the columns. So that's what we're going to be doing today. And therefore, assignment number 6, it will be a continuation of assignment number 5. I simply broke it down into 2 assignments, but on the test, this diagram would apply to 3 questions. So, okay, so slideshow from the beginning. Okay, so I hope you guys can, at least understand that this is an elevation, okay? And basically what I'm doing here, okay, is like, for example, okay, normally, for example, like I didn't draw it here, but sometimes what you can have here, for example, you can have, a picture window, you understand? And I didn't bother putting down the closing, but this doesn't matter whether it's closed or not. This is what's going to basically determine the span of this beam. And here you can have another opening and so on and so on. And I will go over this on the assignment, not the assignment, on the project where you have something very similar to this, where you have a door and a window, and that's going to be the one that's going to be the column that's going to be the most critical, and so on and so on. So here, basically, I'm looking at a cross section or an elevation of the house. Okay, the house is spanning, in this case here, the trusses are spanning 8 meters. And you just have to remember that in theory, okay, half the load goes there, half the load goes there, and therefore this from here to here becomes a tributary width that is going to be brought to this supporting a member here, and therefore you'll be able to calculate the loads that are being transmitted along the wall here, okay? So that's what you should be starting to visualize a bit in your head. And for figure 1, I say design, this thing is in my way here. So I say design the exterior bearing wall, use SPF number 3 stud grade 38 by 140 lumber. And the reason why I tell you to use 38 by 140 is because you need to carry the cavity so that you can, put the insulation and have the thermal resistance that the wall is required according to the energy requirements. It's a law now. So the architect is the one that would be, concerned about that. But that's why we would use a 2x6 more to accommodate the insulation for the wall than for structural reasons. Okay. Now, the advantage of using 2x6 is because they're stronger studs. You can space them a little bit further apart than the 2x4, but basically it's more done for the insulation than anything else. Now, the studs are effectively pinned and laterally supported at each end, okay? Buckle prevented by the weak axis by the wall sheeting and fastened to meet the requirement of case 2. And I'm giving you all this so that you can remember that you can go straight to the tables and look for the values of PR and WR to decide whether or not the 2x6 will be sufficient. And of course, if ever all this means is that if you are designing something and this is what you want to use, and you're actually going to have to specify on your drawing what a case 2 system. You can't just simply say case 2. You would have to specify what the nailing requirements is and the thickness of the sheeting that has to be provided in order to get this case 2 system. Okay. So that's something that you have to specify either on the drawing or in the specifications. Now, here the dead load is 0.6 kPa, which is reasonable for a residential roof. The snow load 3.0 kPa, a little bit more in Montreal. And of course, here the wind pressure is 1 kPa. That's for strength. And of course, because of the importance factor, when it comes to serviceability, it goes down to 75. So in other words, you take 75% of this value for serviceability. And normally, because your walls will have drywall on the inside, you tend to limit the deflection to L over 360 because a drywall gypsum board, when I say drywall gypsum board, is susceptible to cracking. And if you limit the deflection to L over 360, you should hopefully minimize any cracking that the drywall might be subjected to. And of course, we have dry surface conditions. It's going to be a wall. It's going to be untreated. And of course, the studs are concentrically loaded because the truss goes right over the wall. You can assume that the stud is concentrically loaded. And therefore, you don't have to worry about that other column where you have the eccentricity. So now so now here, what I'm going to do is, like I'm going to have a case 1. I'm going to factor load for case 1. And of course, I'm going to have case 3. So, and of course, in this case here, case 3 is the one that governs, okay? It's much higher than just case 1. It might seem redundant, but I'm just repeating this so you remember that there's at least 5 case combinations for the loads. Now, keep in mind that here, okay, the main difference is that the snow is the principal load and the wind is the companion load. Okay, so that's why we have this. This is principal load, companion load. That's for case number 3. Now in this case here, we're looking for PF. Well, PF is equal to your factor load times your tributary area. So all you're looking at is that, okay, so here's your wall. Your studs are here. Okay, this is your studs. Okay. So basically, what's your tributary area? Well, you know that the spacing of the studs is going to give you the tributary width in one direction. And then from the center here of the building, so this is your tributary area. So therefore, that's your tributary that each stud is going to be carrying. So therefore, half the roof span plus the angle plus the stud spacing should give you your tributary area, assuming that the roof truss is spanning from exterior wall to exterior wall, which is usually the case. And therefore, I end up getting a tributary of 2.7 meters. Now, PF is your factor load times your tributary area. It gives you 14.2 kilonewtons. So that's for your axial force. And now for the wind, you know that the table you don't have to calculate MF. You simply have to calculate the factored wind load. And therefore, the factored wind load is equal to times the stud spacing. In other words, if I look at an elevation here, okay, here are my studs. Okay, so each stud is going to have that tributary width, which is of course the spacing that's going to be acting on it. And that's going to give you your WF on each stud. So, yes.
The stud spacing is 600 millimeters.
Yeah.
Oh, yeah. Never mind.
Okay.
It's my mistake.
Not a problem. Like guys, whenever you're using 2x6, you start at 600, okay, 24 inches. And if for whatever reason doesn't work, you don't change your stud size. You just reduce the spacing. By reducing the spacing, you'll be reducing both PF and WF, and therefore you might go to 16 inches. And if that doesn't work, you can go down to 12 inches. You understand? So you start at the let's say, I don't say the furthest, but let's say that if you want to take advantage of a case 2 system, you cannot exceed 610 millimeters. So you start at 600, which is 24 inches, go down to 16, then go down to 12. And if it doesn't work at 12, well, just double your studs. That's all I can tell you. You understand? So now here, this gives me my WF. Okay, remember this is your load factor 0.4 because it's load combination number 3. And of course, this was the pressure that was given to you, but you know that you'd have to actually calculate this from your wind load equation. And of course, this is your tributary width, and that's what we say the stud spacing. So we got 24. Now that we have PF and we have WF, okay. Now we did it for case 3, and of course we have to now go look for case 4. Okay, this doesn't change. This I repeated it here, but case number 4, of course, is where the snow load becomes the companion load and the wind load is the principal load, okay? And like I said, I hate the way they write it in the books where you get 2.5 D plus 1.4 W and 0.5 S. That is totally wrong. You do not add a horizontal load with a gravity load. So that is, like this is very misleading the way they show it to you. So, somebody was about to say something before?
Yes. Maybe I missed something, but why we are isn't the wind load it's 1 kPa?
1 kPa, yeah. That's right. So here, all I'm doing is that right now I'm just calculating the gravity loads right here. In other words, right
So
here,
what is this 1.4 multiplied by 0.6?
1.4 multiplied by 1.0 kPa, kilonewtons per meter squared, times the tributary width, which will give me my
Okay,
WF.
this is the
You
I'm
understand?
sorry, because I thought this was 0.6 kPa, not not
No,
meters.
that's
Okay,
that's
my
the
bad.
spacing. In other words, that's the tributary width that each stud is carrying. Understand?
Okay.
So this is the load factor. Okay, this is the load factor, and therefore you have to multiply your specified load by your load. These are called load factors, guys. 1.25, 0.5.
Yes.
These are called load factors. That's your load factor.
Yeah.
In other words,
I was talking about the first line where it says factored load 1.4D.
oh, because this our dead load was 0.6 kPa. It's this one here.
Yes. Sorry.
So okay, so that's what
Okay.
was confusing. You saw 0.6
So this
kk
is.
here, then I multiply by 0.6 meters on the other part, right? So
Uh, I thought this is for the wind load.
no. This is just for load
Just
combination
yeah.
one. Okay, sounds good. Thank you for
Okay. Fine.
Okay. And now, of course,
My bad.
guys, this to me is just common sense equation. Whenever you want to calculate your PF for anything, any member that's in compression, your PF is always your factored load multiplied by once you determine the tributary area that member is carrying, then you take that area, multiply by your factor load, and you're going to get your PF. In other words, your factored axial force that is the member has to carry. And now, of course, in this case here, it's exactly like as before, half the roof truss plus the overhang plus the stud spacing, okay? And of course, the same area. I just repeating it here because I cut and paste this, right? It's not that I retyped it. So here I end up now, of course, for case number 4, of course, the PF is going to go down, but what's going to happen is the WF is going to go up. So in other words, you have less axial load, but you can have more bending, okay? So therefore, you're going to try to find to make sure that your stud can satisfy both load combinations. Now the WF is your wind load multiplied by your spacing. And now here, 1.4 as opposed to 0.4. And then of course you're up to 0.84 kilonewtons per meter. So now that I've got my, I forgot the other PF, but guys, I'm gonna, because I don't remember, okay? So now I have to know what my stud length is, of course, so that when I go into the table, I'm looking at the right values. And here, I don't remember, sorry guys, I should have written down, I didn't write down the value, so I'm not really sure what I'm looking for. Can anybody tell me what PF was for the load combination 3 off the top of their heads, or?
14.2.
14.2? Okay,
Yeah.
so basically guys, what I do, okay, is I start with case number 3. I look for a PR that is greater than 14.2. This is good. And then I come over here, okay, and of course I'm not here at all because I'm concentrically loaded, and I make sure that the WR here is greater than the WF, and I believe it is for case number 3. Am I correct? What was
Sir,
it?
I have a
Pardon?
question about this table.
Okay.
Yeah, you're correct, sir.
Yeah.
My question is, I don't understand the difference between each line because I get we're using a 38 by 140, but for example, we have 14.2. If we would have, what if I chose, I don't know, 20.2? What difference does it make?
Oh,
Still using.
it doesn't matter. See, because look what happens, okay? Let me explain to you the table, okay? What the table is doing is, okay, first of all, I'm not going to write the whole equation, but you understand that this table is PF over PR, right? And of course, it's wood, so this is squared. Plus, this is the interaction equation, right? MF
Yeah, I
over
get that.
MR,
I
okay?
get that equation.
Okay, so what happens here is that what they're doing here is they're saying, if my PR value goes up here, okay, well, I'm going to have to reduce my MR value in order for this to be less than or equal to 1.0. So what they're giving you here is a range. So for example, if I can take 20.2, as long as this WR is greater than my WF, I'm still okay.
Okay.
You follow what I'm saying? So for example, if you tell me that, what I do is I tend to look for the PR that is slightly equal to PF, so I can have the maximum WR for this side of the equation. But if you say 20.2, is this still greater than Is this still greater than what we had for load combination 3? What was the WF for load combination 3?
It was 0.24.
There you go,
Yeah.
0.24. So is this good? Yes, you understand?
Mm-hmm.
As a matter of fact, this is still good. You understand? This is still good. You follow?
Yeah.
So what this is saying is that all of these are good for our load combination 3.
Okay.
But
Thank you.
you understand? But what all I'm looking for is a PR slightly bigger than my PF, so I can leave the maximum for this side of the equation. Because if you
Okay.
start going for the higher values, you start reducing what you have for this side of the equation.
Okay. Thank
Is
you.
that clearer?
Yeah, it's clearer.
See, so like you can appreciate that if I have a very small PR, well, I can have a very big bending moment. You see? So in other words, if
Yeah.
I have a small PF here, my PR has to be slightly bigger than, and therefore I leave a lot of room for bending moment. And then the opposite is that if I have a big axial force and I have a lot of bending, well, then I can go down here and I can still see if it's okay. So all they're doing is they're giving you a range of what this equation can do. This is they're giving you the, like if this goes up, then this goes down. If this goes down, then that goes up. That's all they're doing. Okay. But you're
Yeah,
absolutely
thank
right. In other words, if I come here and I pick this, if this works for my load combination 3, great. If this works for my load combination 3, great. You understand? But I always try to find the PR that is close to my PF to leave the maximum MR that I have for my MF.
Okay. Thank you.
Is that clear?
Yeah, it's clearer now.
Okay, like so don't worry about that. Okay, so in other words, if you would have told me PR is 23.6 and WR is 4.39 and the PF, you know, PR is less than greater than PF and the W, it's still good. You understand? The answer is correct. So that was for case number 3. Now for case number 4, I believe that I don't remember what was the PF value for case number 4.
6.1
6.1. So therefore I can go all the way up here, right, for my PR value, and I still have a big WR value here, which I don't think we've exceeded.
Yeah, that's correct.
What was the WF value for case number 4?
0.84.
0.84. So in other words, I could have gone right up to here still, and I could have satisfied both conditions. Do you agree?
Yes, sir.
Okay. So that's why. But if all of a sudden I want to choose this wouldn't work anymore. Because then if I would take this condition here and I would actually do it with the equations, I would get a ratio greater than 1.0. So that's why. So look for a PR value that is slightly higher than your PF value. Then just make sure that you're going to go get the maximum WR value to offset your WF value. That's how I tend to do it. Okay. But all these answers here satisfy case number 4. Okay. So there we go. And that's, I hope that clears up the table. So for case 3, PF is 16.9. And of course, that gives me the maximum WR. And this is great. So I can, you know, and then for case number 4, 6.75 greater than 6.1. And therefore, this is greater than that. Great. They're both okay. Therefore, a 2. You check the bearing. So yeah, the QF has to be greater than the PF. That's what the bearing is. And therefore, you simply go to the bottom of the table. Okay, we go to the bottom of the table. And we find the value of QR here. Oops, sorry, 32.4 kilonewtons. You get it straight from the table. And therefore, the QR is greater than the QF. Great. That means my sill plates, or my sill plates, the top and bottom plates, I shouldn't call them sill plates. My top and bottom plates aren't going to get crushed underneath this load. Perfect. I check for shear. Now, for shear, you just have to remember that you take the wind load from case number 4, because that's the highest bending moment. And that's what I'm taking here, the wind load from case number 4. And of course, I go here and at the table, I get my VR value of 10.6 kilonewtons. So I know I'm okay for shear. So, which is great. And now last thing is for my deflection. Now I take 75% of, or in this case, since it's 1 kPa, 0.75 kPa for my serviceability, and I still multiply by my tributary width to get the specified wind load for serviceability with 0.45. And just like before, like what we did for beams or anything else, just because it is a vertical member, okay, like this, and it's pinned here, and it's pinned there, and I have a load here, well, that's, the analysis doesn't change at all, whether it's in this direction, because it's going to be bending this way, or as if I would put it in this direction, okay? So therefore, it's the same equation and everything, and therefore, we will now, understand, we calculate that the ESI required is 33.3, and now you don't even have to go and calculate the ESI required. It's right at the bottom of the table also. And here it is. So for a 78.2 times 10 to the 9 Newton millimeter squared. And so that's good. And that's it. So there you solved your first part of an exterior wall. You've managed to say that. Now, keep in mind, guys, I'm going to say this once, okay? Like once you've decided to make, excuse me, once you've decided to make your exterior wall, okay, once you decided to make your exterior wall with 2x6s, okay, that's going to be your exterior wall. Well, any built up columns that you're going to be putting in this wall will also be made with 2x6s, okay? So you use the same size lumber to make up your built up columns, whether you need 2, 3, you don't go and then make built up columns out of 2x4s in a 2x6 wall. They use always the same stud size, okay? So that's something we're going to be doing today. So now that we decided that 2x6 is appropriate and can be spaced at 24 inches on center for the loads that are involved in this particular project, now we're going to go ahead and start designing the lintels and the built-up columns. And for the built-up columns, we're going to be using exactly the same stud size. So for assignment number 6, you're going to be using 2x6 stud size to size your columns. Okay. Okay. So, yes.
And you just go back to the step where you check your shear.
The shear, yeah. Go ahead. Shear here, yeah. WFL over 2. This comes from load
Yeah, how
case.
did you get the 2.5 meters?
That's the length of the stud. Okay, so in other words, this my wall is 2.5 meters high. I think I gave that. Is that what I said?
Oh, okay. Yeah, I took the wrong value. Yeah, never mind.
Okay, and therefore you assume that if that's the height of your stud, that's going to be the span of your stud. You understand?
Yeah. Okay.
Did I make a typo here, guys? I don't think so.
No, it's correct.
It's all good.
Okay, it's
I
all
took
good.
3
Thank you.
meters. I took the yeah.
You know, I mean, guys, I do a lot of typos. Trust me, so don't worry about that. I expect between 35 students, we can pick them all up and correct them as we go along. Okay, so that's good. So we're all done here. Okay, and like I said, it's once you start getting the gist of it, it's like you'll see that a lot of these steps are somewhat repetitive, even for the built-up columns. Mind you, the built-up columns, unfortunately, we cannot go to any table. Well, we can to get our PR value, but then there's a few other steps that we need to do. Okay, so that's it. Let me just stop sharing this.
Sir, I have a question.
Yeah, hold on. I just want to make sure that I close this one because I don't want to see that anymore. Go ahead, Jan.
Do we need to check the bearing every time for?
Yeah, well, yeah, like what you here. Let's just make sure we're on the same page. Okay, we'll use the whiteboard. Okay. See, basically, when you're designing a bearing wall, okay, normally a bearing wall, for example, this is your floor here. Okay, in other words, you got your studs. Okay, this is your not your studs. You got your floor joists. You understand? And they're hopefully your floor joists are sitting on some kind of a sill here. Okay, and so on. And then you have your plywood. Okay, whenever you're building a wall, the first thing you do is you put one bottom plate here, which is the same lumber as you would use as your stud size. In other words, this would be a 2x6. In other words, these 2x6s, they come in 16 feet lengths. Okay, so you would be buying 16-foot lumbers. This would be your bottom plate. Then your studs are sitting on that like this. Okay, at every 16 inches. And then on top of here, you would have 2 of them. Okay. Now, when the carpenters are building this wall, they'll nail this and they'll nail this. This is how they build it. They nail all of this together. They nail it on the floor and then they tilt up the wall. That's how these things get built. Then once all the walls are built, then what they do is once all the walls are built, for example, here, this is one wall here like this, and at the corners here, okay? So for example, that's one wall, and they just have one plate. Then what they do is they go ahead and double the plate. And what they'll do is that then they'll take this top plate here and they'll bring it over here so that it locks the corner properly. And then they'll make this one come butt up against it. Okay, so that's how these things are actually, that's how the second plate is added on. So that when the carpenter comes and he nails this, he's kind of like made sure that he's bridged that joint there between the two walls. Okay. And then on top of that, I can get into a lot of details, guys, if you want. Okay, and on top of that, when they do these anyway, I don't want to get into it. It'll just confuse you. But I can show you a lot of details that you can do for wood framing. Okay, as a matter of fact, when they do these corners here, okay, when they do this corner here, like for example, if this is a corner here, okay, this is a stud here, and the corner, and then you know that the next wall, excuse me, you know that the next wall is going to be coming right next to it here, like this, okay. And so on. Well, what the carpenter is going to do is that right here on this stud here, okay, he's going to nail another stud here like this, okay, and he's going to make like an L. So therefore, when he puts up the next wall, when they put the drywall is going to have two edges that they can lean on to install the drywall. So you always make an L in the corner here so that when you come and install the drywall has a backing or a support that you can attach your drywall to. So you'll see a good carpenter will realize that if this wall is going to be up against another wall, he'll always use he'll just nail here the stud, and that's already going to be part of the wall. So this way, when you're ready to do the drywall has a backing. Okay, so there's a lot of little details that you guys will eventually see when you start looking at wood framing. And good carpenters, they know this by practice. Okay, so you don't have to worry about it. Oh, yeah, Jan, I really diverted there. So Jan, you're talking about, so therefore you want to make sure, okay, you want to make sure that when you, okay, you want to make sure that when the load is being transmitted through these studs, okay, you want to make sure that this thing doesn't crush on you. Okay, you want to make sure that you don't have any crushing here, and that's what the bearing's all about. Okay. Now, the reason why you take the values at the bottom of the table is because you do not use that equation LB required is equal to QF over small QR, because here you can take advantage of the fact that this is wider than this, and therefore there's an amplification factor for the QR value. I can show you how they do the tables, but just go get the value in the table, and it gives you the value of QR based on the fact that the bearing is like here, the bearing is acting at a width wider than the depth, and there's an amplification factor for that. That's in the table that I gave you for bearing. So that's why just use the value in the table, and that's going to be a QR value. Now, I noticed, I'm going to say this very quickly, okay? Somebody sent me their design brief. I won't say who, okay? And I mean, I don't mind doing this, okay? But for example, what the person did, I thought it was very conscientious, but it's somewhat mechanical, okay? When it came to this member here, okay? This member here in your truss, okay? In other words, a small compression member here, right? Well, they went to calculate the QR against the stud here. First of all, that would not be the right QR value, because in this case here, the 2x6 is in that direction, it's not in the flat direction. Secondly, the reason why you don't worry about QR here is because when we put the gusset plate, when we're going to be designing the plate, the force are going to get transmitted through the plywood and not be bearing on the surface here. So you don't have to worry about the QR when it comes to trusses, because they go through the truss plates. They don't go through the members. That's why you don't have to worry about QR. So I don't know if you guys looked at QR when you're doing that little part, but I didn't want to say anything. I thought it was really nice, but it's like understanding, like I was going to explain this in the joints, that you don't have to worry about the QR because the actual force is going through the plate, is not going through the member, versus when it's just a wall well, it's going through the member and right into that surface, okay? So for example, if I would put plywood here on this surface here, and I would nail this to hell like this, okay? And I make sure that nail, I have to, okay? And I nail it here, well, you know that you don't have to worry about QR because that whole force is going through the plywood, you understand? So I just wanted you to, so I thought it was interesting when I saw that in the design brief, but I was going to explain that to the person, but I figured it was going to be more confusing than enlightening, you understand? So I didn't want to bring it up. Okay, so now we're going to continue with the lecture. I hope I didn't bore you guys. I hope you find this interesting somewhat, it's up to you. So Jan, does that answer your question? I'm sorry.
Yeah, yes, thank you.
Okay. So, do you guys see the screen? I'm sorry. Am I sharing the screen properly? I'm sorry.
No,
We see
can see
your
the
desktop.
background.
Oh, you see the background. You see two ladies in the background?
Yes.
Yep.
Yeah, those are the other two ladies in my life. Pardon? That's my daughter and my granddaughter.
So you gotta clean up those icons.
Pardon?
You have a few icons on your desktop there.
I have a lot of icons on my desktop.
Yeah.
Well, I mean, I use my computer quite a bit. You understand? I should get rid of these PDFs. that I should do. You know,
Yeah,
I agree. And I should get rid of the older TurboTaxes. I agree. So
yeah, I think everyone's desktop this semester kind of looks like that. So
yeah, and it just slows on your computer. I agree. So you're absolutely right. You're absolutely right.
You haven't got rid of TurboTax since 2014. Not to judge you here, sir.
Pardon?
You haven't gotten rid of TurboTax since 2014. I'm just
wait, David, I was good. I got rid of 2011, 2012. So I've been good. I got rid of a few of them. Okay, so let's leave it at that. How's that? Okay, but I don't know. For some reason, I'm going to clean it up. You're right. It's okay. So guys, today we're just going to continue with the exterior walls. Okay. And we'll talk about lintels and exterior columns. And it might seem complicated, but it shouldn't be that complicated because the equations we've seen already in one of the lectures, the interaction equation. Now, I'm not sure if this is a continuation of the example I did in the first class, in the previous class for the exterior walls. I'm pretty sure it is, okay? I'm pretty sure that this is a continuation, even if it isn't, okay? Basically here, what we're looking at, let me just, I'm going to make sure I can annotate. Okay. So here, guys, what's happening is that, okay, so we've designed these walls in the previous class. And now what's happening here is that most likely this house is going to have like here, a picture window in here, which is about 8 feet high. And this is to accommodate some kind of a man door, understand? So therefore, when they're going to be framing this, they're basically going to leave this, you're going to have to be able to take all the loads that come from the roof and transmit them to these columns here. And the same thing here. And keep in mind that this column here is going to be carrying the loads from that much of the beam and that much of the beam. That's all going to be going on to that column. And then on top of that, not only is that column going to have an axial load, a gravity load going through it, it's also going to have the wind load that's going to be acting on that column. So you have to worry about, you know, again, combined loading, both bending and axial load. So that's just to give you a quick overview of what we're heading for. Now here, 0.48 kPa, okay? I mean, these are reasonable values. I mean, this is probably down in central Ontario, you know, this 2.0 kPa. In Montreal, I wouldn't design anything less than 2.5 kPa. The specified wind load 1 kPa, which is reasonable. And again, okay, so like I said, if ever you're doing this, you're always going to have to calculate these based on the climatic information of where your house is located, and that's where you get all this, except for this, okay? Everything else comes from the climatic information in the National Building Code. I don't know if you guys are interested, but I have, see, the National Building Code is very limited when it comes to being very specific. If I can find it, if you guys are interested, I can send you a document that gives you the snow loads of almost every town in Quebec, which is nice to have. If you guys want to have that, just let me know. And if I can dig it up, I'll be more than happy to share it with you. And that's, you know, because if you happen to find a town that's not in the back of the National Building Code, if you want to get the information, it's going to cost you about $300 if you ask the Environment Canada for that information. It's up to you.
I mean, yeah, why not?
If I can find it, Omar, I'd be more than
please.
happy to share it with you. I mean, like, because And as a matter of fact, if you go to Sicobois, they provide that information. They're the big lumber association in Quebec, Sicobois. I'll try to get you the name, or I'll try to find a table and I'll get you that information to you guys. Okay. Okay. So I diverted a bit. So, but here we go. Now, so guys, this is the geometry. Like I said, no geometry, no design. First thing you have to establish is geometry. And then once you've established your geometry, you have to estimate your loads. Remember, these are estimates. They're not exact values. This is a good estimate. 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 So this, and then once you've got your geometry and your loads, well, the next step is your analysis. And once you've done your analysis, well, you size your member, you design the member size. So here we go. So now keep in mind, okay, whenever we're looking at tributary widths, okay, so for example, for the gravity load, the tributary width will go from there to there. And that's the same thing for here. And when we're looking for lateral loads, the tributary width for this column would go from there to there. Okay, so I don't know if I'm going to be able to come back to this diagram, but this is what we mean by the tributary width for here, and this is going to be the tributary width for the gravity loads. Okay, I just want you to keep that in mind so that when you see the numbers, you can relate to the figure. So now, again, okay, case one, I always put it down more for this here, guys. Like I said, I keep doing it for academic reasons, okay? Because I can tell you right now that if the dead load does not exceed 10 times the live load or snow load, case one will never govern, just to let you know, okay? And I can show you that mathematically how I came up with that value. But this is just a reminder that you have to worry about when, like, especially in reinforced concrete, where concrete is very heavy, sometimes the dead load will govern your case load. So, but in wood and steel, very, 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 very rare that that's the case, unless, you got 3 feet or 4 feet of earth sitting on your structure. Okay, so now case number 3, okay. Of course, here again, okay, case number 3 is the snow load is the principal load and the wind load is the, companion load. Okay, so now, oh, sorry, we're designing the lintels. We're not looking at the column here. I apologize. Okay, so you're trying to determine the gravity load, and of course, case number 3 is the one that's going to give you the higher gravity load versus case number 4. I won't even bother with case number 4 for the gravity loads. Now, WF is equal to your factor load times your tributary width, okay? And here I say half the span plus the roof overhang gives you your tributary width. So if you go back to the diagram here, do you guys prefer me doing the slideshow, or do you want me to show it to you per slide? How do you guys want it?
What do you mean? What's the difference?
Per slide, I think it's better. Like, I feel like
You like this better than the slideshow? It's up to you. Whatever you guys think is more, because I can, because this way I can maybe click back to this slide here and we can go back and look at the geometry. You understand? It's up to you guys. Whatever you guys feel more, it'd be more easy to follow. You guys tell me, you understand?
Oh, it's fine like this also.
You like the slideshow?
Yeah, it's good.
Well, good. Which one is good? The slideshow or the per slide?
You said like this is okay.
It's okay like this because, I went through the whole trouble of animating this. I might as well use a slideshow. It's just that by the slideshow, you can just concentrate on one line at a time without getting distracted. Okay, I'm going to do the slideshow. I'll do the slideshow. I went through the trouble of animating this. So, okay, now, again, this is typically the tributary width, because the truss spans from exterior wall to exterior wall plus the overhang. Okay, this is something people tend to forget, the little overhang. And of course, I get a WF of 18 kilonewtons per meter, which is great. Now, guys, what's a lintel, basically? What's another term for a lintel?
It's a beam?
It's a beam, all right? So what choice do we have when it comes to beams, okay? So guys, when you guys were designing the built-up beams for the floor, you're doing the same thing for the lintels. You're going to be designing a built-up beam for the lintels. That's what we normally do, okay? Unless they're extremely wide spans and you don't have the room to put like 18 layers or plies, I should say. So you're just basically designing a beam. So this is basically should be a review and not necessarily a new concept. Now here, of course, what I'm doing is I'm calculating the snow load so that I can calculate deflection. In other words, I'm just taking the snow load, just like I would take L times my tributary width. Here I take my snow load times my tributary width. I know that for serviceability, it has to be able to resist 10 kilonewtons per meter. So this is to calculate the ESI. And of course, this is MF is equal to WF L squared over 8. Okay. So in other words, I take the biggest span. Okay. Here I have two spans, right? So what I do is I design for the bigger span here. Okay, whatever, I think this is what it is, 2.4 meters. And then whatever is good here is definitely going to be good for there. So I'm just going to have the same, specify the same built up beam because it's going to be made, you know, probably right through by the carpenters. So I take the biggest span here and I get my MF value. And of course, I take the biggest span to calculate my VF value. Okay, so I have my MF, my VF. And the last thing I need to do when I go select the beam from the built-up beam table is, of course, my ESI value. So there you go. So, of course, I want to keep the deflections to L over 360. Why? Because on the inside over that beam, that wall, there's going to be drywall, and therefore I want to minimize the cracking of the drywall that's going to be installed on the face of the beam. So ESI required is equal to 5WL to the fourth. In other words, I just isolate the ESI. And of course, here, you guys remember that this cancels this, it becomes cubed, and that's it. And we can now find the ESI required, 640. Now, I don't remember, I should write this down. So when we go to the table, 13 kilonewton meter, 21.6 kilonewtons. So when we go to the table, we know what we're looking for. And the ESI required is 648. So here we go. So now I've got my three values that the beam has to satisfy. One, the first two for strength, the third one for serviceability. I go to the built-up beam tables. Okay, and of course, I come here and I'm looking for an MR. Like guys, you're going to be using SPF number 1, number 2. I'm looking for an MR that is greater than 13. So this is pretty good here. This is no good. This is good here. Okay, so I can go with a 3-ply. Okay, with a 2x6 3-ply, or I can go here, or I can go. This is no good. Okay, or I can go with a 5-ply. I wouldn't recommend you put a 5-ply. Okay, so this is good here. Okay, and so that's the MR is greater than my MF, and my VR here 29.2 is greater than my 21.6, so that's good. And the ESI here of 648, well, this is really good. In other words, I have almost twice the stiffness, so therefore the deflection is going to be almost L over 720. So this would be a good choice, okay? And what's nice about choosing a 3-ply is that if you look at 1-ply, 2-ply, 3-ply, okay, this here is 38 times 3, and that gives you what? I think it's 114, okay, and therefore, and your 2x6 wall is 140, so it's going to fit nicely inside the wall without bulging out. So it will fit very nicely inside the wall. You understand? So that's what's nice about a 3-ply. If you go to 4-ply, well, you know, it's going to be a little bit of, okay. So that's a good choice here. So that built-up beam would be SPF number 1, number 2, 38 by 143 ply, and of course you would write down all the MR values. Okay, I hope you guys understood what I meant by the 3-ply would fit nicely into a wall that's 140 millimeters wide, which is the width of a 2x6, and therefore that would be a good choice. And therefore SPF number 138 3-ply, 13 is greater than 13, great, that's all I need. And VF is greater than VR. I mean, VR is greater than VF. perfect. And of course the ESI, it's almost twice. That means the deflection would be just maybe L over 720, which is really, really good. So that would be nice. Now guys, for your general information, okay, for your general information, whenever they built up beams, I just want to show you something. Here's the top plates, okay? Here's the top plates. Okay, here's my built-up beam. So if I ever specify a 2-ply or a 3-ply, you should try to stay within a 2-ply or a 3-ply. What the carpenters are going to do is they're going to add another 2x6 here underneath, so that when they put the drywall, it's going to be able to finish the wall completely here. So there's always another 2x6 put horizontally along the bottom of your built-up lintel, so that they can do the drywall properly on this side. So that's why when you're looking at lintels, try to stay within a 2-ply, try to stay within a 3-ply. If you go to a 4-ply, you're going to have this bulging, and not too many people like to see the bulging coming out of the wall. Okay, and of course here's your plywood. So that's the typical way that they will build the built-up beam. They'll put a 2x6 on the underside. It would be like almost like a bottom plate, but it's more so that the drywall has something to sit on here when they put the drywall. Otherwise, the guy that comes to do the drywall, he say, hey, I can't install the drywall. I got nothing to nail it to. Okay, and at the same time, this gives a completely closed box, so that when they install the window, they can shim and everything. There's all kinds of advantages of doing this. So that's the typical way of framing the underside of a lintel. And like I said, if you're going to make lintels, try to stick to a 2-ply, try to stick to a 3-ply. If you need to go to a 4-ply, I don't recommend it, because it's going to go outside the width of your wall. So I'm giving you practical choices that you should consider when you're considering your choice. And in this case, it works out really well. And of course, if you're going to be using 2x10s, 3-ply for one lintel, and you have a smaller window, and even if you can get away with a 2x8, still use 2x10s. Always use the same size lintels all the way across. Why? Because when they're going to be framing your windows, okay, when they're going to be framing your windows, you want to make sure that the height of your windows are the same right across the whole facade. You don't want to see one window a little bit higher, a little bit lower. And especially when it comes, if it's bricks, you want to be able to put the course of bricks right across there. So that's why you want to make sure all these openings are exactly the same height. So even if you can get, you know, like you might end up with a 38 by 184, don't. Go with, if you started with a 2x10, stick by 2x10s all the way across, you know. And always use at least 2 plies for your lintels, even if you don't need them. Just okay, so that's just giving you some practical information. Now the bearing length, just like we did, okay, just like we did for the beams, okay. LB has to be greater than a QF or a small QR. Now, I didn't go to the table, but this is the value of an SPF. Doesn't matter what grade, they're all the same. It doesn't vary with grades, but I have to remember I have a 3-ply, so therefore I can divide this. This is per ply, right? And therefore I calculate the LB required. And this is where it becomes critical, you understand? So so therefore the LB required has to be at least 45 millimeters, okay? So there we go. Now, so that's the LB required. Now this is for the column, okay? Now the built-up column. We have no choice but to start with the interaction equation. In other words, we have to go calculate our PF, we have to go calculate our PR, we have to calculate our MF, our MR, and of course, this is the amplification factor, the PF, or the Euler's buckling resistance, okay? And this is the only way to do it. There's no tables, no nothing. We just have to be able to find, we have to come up with a trial section, and hopefully the trial section will work. And just like we did, for example, in steel, if this ratio is close, if it ends up being around 0.7, 0.8, 0.9, close to 0.1, it's a good choice. If it happens to be like in the 0.2, 0.3, then you can maybe resize and go something smaller. So here, from case number 3, we know that our PF value is 3.6 kPa, right? That we don't have to recalculate, because the factor loads are factor loads, and the biggest factor load, gravity load, comes from load combination number 3. Now, what we need to do is calculate the PF, and like I said, whenever you need the PF, here's my column here. I don't know what size it is right now, but I know that my column is carrying in this direction the same tributary width that the lintel was, all I need to now determine is what is the tributary width in here. Well, this goes from half the distance between this column and that column, and that's how I calculate the tributary width in this area. So therefore, these two tributary widths will give me this tributary area. Okay, so that's what we're looking at. And of course, like I said, I don't have the sketch. I should have put a link to go back to the sketch, but I apologize. So half the roof span plus the overhang plus half the span of the lintel on the left side and the right side. If you want to remember, mathematically how it is. So it's half the span of the lintel on the left side and half the span on the right side. So I add the two spans together divided by 2. I take half the span of the roof truss, add the overhang. That's going to give me the tributary width. So 9 divided by 2 plus 0.5. So that's for the for the trusses, in the direction of the truss, and this is in the direction of the adjacent openings. Okay, I have 2.4 meters on one side, 1.8 meters on the other side. I add them together, divide by 2, and that gives me my tributary area, 10.5 square meters. And of course, this is my PF, and therefore, now here is, okay, so now guys, keep in mind that you got to give a little bit of, you have to give yourself a little bit of resistance for the bending moment. So don't go look for PR that's very close to your PF value. Otherwise, you're not giving yourself much room here, okay? So now for the trial sections, what you do is you go to the built up columns, okay? And do you remember, does anybody remember what the length of our column is? The height of our wall was? It was a 2.5 meters or 2, does anybody remember? Anyways, all I'm saying,
2.4.
pardon? 2.4?
2.4. Yeah.
Okay, so here we are. So in other words, why don't I want to use this table? Because this is for 2x4s. My wall is being made out of 2x6s, so I don't even want to use this table. I want to use this table here. Okay, that's number one. I want to use a 2x4, and then on top of that, so now you'll notice here I went down to 2.2. Why do you think I went down to 2.2 instead of 2.4?
Do you have less of a resistance?
No, it's not that. The lintel here is
because you're going to cut the stud.
they're gonna be sitting on top. Like in other words, exactly. So in other words, this was the height of the wall, but then this is sitting. So the actual column height here is about 2.2. If you use 2.4, doesn't matter. It's still good, but you can see that right now the length of the height of the column is the height of the wall less the thickness of the lintel, and therefore you can go down to 2.2. So here, like, I'm going to use a 3-ply. I'm going to start with a 3-ply, see if it's okay. Okay, I mean, if I want to be really pessimistic, I should have gone to a 4-ply, but I'm going to feel comfortable here because my PR value is about twice my PF value. So I'm going to feel comfortable as a trial section, SPF number 3, since this is twice my PF value, it's a good starting point. Okay, and if I really want to be, I will not definitely use this because right away it doesn't work. You understand? A 2-ply. Okay, so therefore I'll start with a 3-ply, and if I'm really, like I said, really pessimistic, I will go for a 4-ply, but then it's going to be ridiculous when we probably have to do it all over again for a 3-ply. So that's how I come and choose whether I'm going to use a 3-ply or 4-ply based on my PF value and my PR value. So here I say that use a 3-ply with a length of 2.2. I have a PR here of 60.7. So by going almost twice the PR value, that gives me a lot of room here for this ratio to really, to satisfy this equation here. So that's what I start with. And now, so now I'm going to go to load case number 3, right? And of course, I'm going to, for my wind load. So my wind load for load case number 3 is, of course, the load factor here, since this is the companion load is 0.4 and the WF, okay? And now, what is the wind acting on the column? If you remember, I'll draw an elevation. Here's my lintel here, and here was the other lintel. I should have done it in proportion, but this is like, let me erase this. I'm going to redo it, okay, in approximately in proportion, okay. If you remember that this was, I believe this opening here was 2.4 meters, and this opening here was 1.8 meters. If this is my column here, right? So therefore, this is the width of the wall acting on the column. So in other words, okay, so this is the column and this is going to be the wind acting on the column. Okay, so therefore I take half the span on the left and half the span on the right, divided by 2, and that gives me my tributary width that's acting on this column. Okay, and that's going to give me the WF acting on the column, so I can calculate my MF. So here, so therefore I end up with 2.1 meters. That's the tributary width. And the WF is 0.84 kilonewtons per meter. And of course, MF is equal to WFL squared over 8. And therefore, now, what is the MR for an SPF number 1, number 2, 38 by 143 ply? Where do I find that information? It's not a trick question, guys. Where do I find, like, in other words, how would I calculate the MR for an SPF number 1, number 2, 38 by 143 ply? Where would I get that information?
Don't we get it from the table?
Which table? Sorry?
The beam selection table.
Exactly, the built-up beams. This is exactly the same thing. In other words, now the only problem is that we're going to get the values for number 1, number 2, but what's the real grade of our wood?
Number 3.
Number 3, the stud grade. Okay, so all you're going to do now is you're going to take the value of number 1, number 2, and then you're going to adjust it for a number 3. Okay, and I'll show you how to do that. Okay, so you go to built-up beam tables, SPF number 1, number. Okay, so we come here and we look for SPF 38 by 140, 3 ply. Here's the MR value. So that's where I find the MR value. Okay, but don't forget, this is for a number 1, number 2 grade. So 6.09 kilonewton meters the MR value for number 3. Okay, so now, so that's for number, now, you don't have the handbook, but I would show you where you can find this in the handbook. If you remember, there was that equation, that long equation. This is going back to class number 2, and I know you guys don't go back, okay? Where you get phi FB, anyways, it was a big equation to calculate MR, okay? Since everything is linear in here, okay? And then there was for the big FB, you had to multiply the small FB. So therefore, there's only one variable in this whole equation that will change from a number 1, number 2 to a number 3 is the small FB value. So if I can find the value of FB for a number 1, number 2, and I can find the FB value for a number 3, I can just prorate this value and get the right value for a number 3. And that's like, I would show you where to find that in the handbook, but I don't want you guys to spend $200 just for that. So therefore, the FB specified bending strength, this is the bending strength, okay? For a number 1, number 2, it's 11.8 MPa. So that's how much bending this grade can actually take. And for a number 3, I believe it's 7.0. And like I said, this you find straight in the tables in the back of the handbook, in the standard. So now, all I got to do now is that this value here was calculated with this value here. Okay, so if I divide it by that value, I remove the number 1, number 2, and if I multiply by this value, I'm going to be bringing it up to a number 3. So that's all I have to do. In other words, I adjust the value from the table to represent this bending strength here. So therefore, I take 6.9, I multiply by 0.7 divided by 11.3, because what I'm actually doing, taking away from the equation by dividing by 11.8, and then multiply, and therefore I drop down for a number 3, I drop down from 6.9, I drop down to 3.61. So that's, how much weaker a number 3 stud grade is in bending versus number 1, number 2. Okay, it's significant. So now the reason why you do that is because when you're going to be buying the studs for your walls, you're not going to buy number 1, number 2 for your columns. The carpenter won't even change. He'll just put the same stud all the way across, even to do his built-up columns. So and first of all, the bundle of 2x6 is all going to be the same grade, and that's why you design it for a number 3 stud grade. So this is the value of MR, and that's how you adjust the value from the built-up beam tables, and from a number 1, number 2, you simply modify it based on these small FB values. Okay. Now, so that, and that's all we're doing. So by doing that, I can now very quickly, I have my MR value. Okay, I have my MF value. Now, the last thing I need to calculate is, of course, the PE value, which is E05I KEL squared. Now, the E05 for a number 1, number 2, okay, excuse me, okay. This is, like I said, this, don't worry, this is the value of E05. This, again, you get out of the tables in the back of the handbook. Of course, we all know what pi is. Now, the moment of inertia, well, it's very simple. I have 3 studs, okay, and they're bending about this. So this is the base. So there's 3 times 38. That's my B. And my height cubed is the 140. So that's the moment of inertia. That's all this is. And of course, the moment of inertia with respect to the centroid at the center of the member is 112. If you remember, I is equal to 112 B times either D or H cubed. And that's what this is, okay? And of course, the length, now, I brought it down to 2.2 meters. And of course, I put it in millimeters. And that gives me the value of PE, which is Euler's buckling resistance for, in this case. And now, once I calculate that value, of course, I've got all the values to check the interaction equation. So I put PF over PR, okay, MF over MR and all that. Now, guys, in my days, believe it or not, this equation, this was not here, okay? And of course, it made this much more severe. I don't know if you guys realize this, but when you take a decimal and you take the square of it, it only becomes smaller. So this really helps you in your case. But in my days, we didn't have that. So that means that they've modified this for whatever we designed in the old days. It was that much more conservative. But just to let you know that if you go to old handbooks, if you don't see the squared here, that's because they realized that the knots in the wood help to increase the strength, and therefore they by and that's why they came up with the square here. And this is only for wood, okay, keep that in mind. So now I put in the values, okay, and of course, so here, this is the value here, okay, this is the value here, and I get 0.55. Guys, as long as I get a ratio less than 1, I'm happy. Now, if I wanted to, I don't think that a 2-ply would work, because a 2-ply, I think the PR value and the PF value are very, very close and doesn't leave much for the MF value here. So right now, first of all, remember, this is only case number 3. We have to check it also for case number 4. So for case number 3, so far, so good. Our trial section is good. And therefore, before I jump, I'm going to go now check for case number 4. Now, the only difference now is that the PF value is going to go down, but the MR value is going to go up because the wind load is the principal load. That's the only difference. So here, my PF value is going to be smaller, okay? So remember, like, you're going to have to recalculate your factor load here because this is a 0.5. I apologize. This is a real typo. I should have put S here, okay? This is snow. I apologize. This is snow, okay? So that's an S, and that's a real typo. So 1.4 times W, and of course your wind load goes up substantially from 0.4 to 1.4. It's 3.5 times what it was initially. And now PF, this doesn't change. Whatever tributary area you calculated for case number 3 is going to be the same tributary area for case number 4. The only difference is that your factor load is going to be a little bit less than half of what you had before. And therefore, that's the only thing that changed. We went down to 16.8 as opposed to before, I think we had 37 or 38 or whatever it was. Now, this goes up significantly because the wind is the principal load, no longer the snow load. And therefore, we're up to 2.49. And of course, here, we need to calculate the MF based on this. We're up to 1.78. And now we can, now guys, as far as the MR values, they stay exactly the same. You don't have to change them. Understand? Because whether it's combination 3, combination 4, MR, PR are exactly the same. So we got from the previous, okay? And of course, all of these values stay exactly the same because these are the resistance of the materials. They've got nothing to do with the analysis. And therefore, we can just take these values here and put them in the interaction equation and check to see if the ratio of both the PF over the PR squared, MF over MR multiplied by this amplification factor here, if it's still less than 1. And of course, okay, we put in all the values. and now I'm up to 0.63. You see, so therefore, what this tells you is that load combination 4 is a little bit more severe in terms of how it's going to impact the resistance of the material than load combination 3. So the wind load here brought the ratio up to 0.643, and we're okay. So that means that as far as we're concerned, as far as being able to resist both wind and snow load, this a 3-ply 2x6 would be ample, because we're like, look how much more room we have until we get up to 1.0. So therefore, this gives me a lot of breathing space in terms of making sure that I can have additional resistance. Now I check for shear. The same thing like we did for a single stud, we'll do it for a built-up column. So how do you check for shear? You take the wind load like we did for the stud. We always took the wind load from case number 4 to calculate shear. So 1.4. This was the WF that we had, right? Now, I don't know why I took 1.2 meters here. I should have been taking I should have taken 1. This should be 2.2, guys, not 2.1. I apologize for that. Anyways, and therefore I get a VF of 3.24. Here, you see, I took 2.2 and I made a typo here. I apologize for that. Now I go back. I don't have to do no calculations. I go back to the wall, okay, and the VR stays the same here. Okay, 10.6, but don't forget that that's for one stud. So if it's good for one stud, could you imagine how good it is for 3 studs? Okay, I have 32.4, which is way greater than 3.24. I know my shear is ample for this column, okay? And like in most cases, people, like I could tell you, people that are doing this constantly, they realize that it's always good to check, but you can see why people don't necessarily check for shear all the time, because look at this, 32 versus 3.2. It's almost 10 times stronger than what you need. And of course, deflection is just as important. So what you do is you check for deflection. The wind pressure, now you use 0.75 instead of using the 1.0, because you're just checking for serviceability. In other words, you take the importance factor, what brings this down to 0.75 because of the importance factor. And of course, now I get this is the specified wind load, and that's why I put a W here, 1.58. Again, this should be 2.2. I apologize. I don't know why I did that typo. So here we go. And I calculate the ESI required. So, okay, 78.8. Now, how do I calculate the ESI provided? Well, I go back here. Okay, I mean, I could have calculated the long way, 1/12, but I go back here, I take the ESI for one stud, and because the equation, so here is the value for one stud, the ESI, that's for one stud. And if you remember, this is for one stud, okay? So therefore, if I have 3 studs, okay, if I have 3 studs, what happens is that it's 1/12 the base times the height cubed. Since the base is linear, and this is 3 times, I could just multiply this value by 3, and that's going to give me the same value as if I would use the equation. That's why I'm allowed to do that, because it's the B that changes, not the H. If it was the H that changed, I cannot do this interpolation, okay? Keep that in mind. So therefore, that's it for there. And so I take that, multiply by 3, I have 203.4 as opposed to 78.9, okay? And like if people look at this, say, well, if I looked at for one stud, it wouldn't be enough. But no, I don't only have one stud. This is per stud. I have 3 of them, so I'm up to, and therefore this would be ample to keep the deflection in check. I mean, and therefore, and as far as the bearing goes, well, this is where you have to check the bearing, okay? So basically, QR has to be greater than QF, and of course, from load case number 3. Now, go back to here, okay? I don't have to do nothing here. All I have to do is come here and look for my QR value per stud. Okay, I have 32.4 kilonewtons. This is per stud, okay? See, it says it here, per stud. And therefore, I take that, 92.7 is greater than 37.8, I'm okay. Now, the last thing you should check, okay, is the bearing of your beam onto your column, okay? That's just check that the column on the sill plates. Then for the built-up beam, okay, we have 3 okay, so what I'm doing here is I'm saying, here's my built-up beam like this. Okay, here's my built-up beam like this. Okay, and here's my built-up column. I have 1, 2, I have 3. Okay, so this is the length I have here. This is the LB provided, which is what? Which is 3 times 38 divided by 2, which is 57. So in other words, I have an LB here of 57, LB provided, and from what we calculated before, 45. So I know that the bearing of the beam on this lintel is ample. Okay. Now, if you would have a problem, because the bearing here is longer than the bearing here, you can also have specified that this one would have to go up to here, but that's not the case. The carpenters will put it right in the middle. So in this case, it doesn't matter. The carpenter, if they put the column right in the middle between the two beams, it's still ample because I have 57 available and 45 required. So as far as the built-up beam goes, it's ample. And I think that's it. So now you've designed everything. You've designed the lintel, you designed the column, you've checked the bearing, both for the sill plates and for the beam. And of course, that's it. How's that, guys? Was it not too overwhelming? How was it?
It was
Not
okay.
bad.
All
Yeah.
good?
Good.
Okay. Now, I don't think you
Sir.
guys are going to like the next sentence.
Do you have
No.
any come next week?
Yeah, we saw it coming.
Yeah, well, I mean, like, guys, I asked at the beginning, you weren't all there, but I asked if you guys had a lot of tests next week. It seems that you guys don't have a lot of tests next week, so it would be a good way to get number 2 out of the way. We all agree? Okay. Now,
Yeah.
Sir,
yes, David.
when's the next steel test again?
Uh,
Since we had the second one early, is the third one earlier too?
There's no fourth. It's the last one.
David, I don't have a schedule in my head right now. Sorry. Why?
Okay.
When do
I
you
was
want
just
to do?
curious.
You want to do it next week, the steel test?
Yeah.
I mean,
No.
It's going to be.
say
It's
no
going
for next week.
It's going to be at least 3 weeks from now. You understand?
Okay.
Why?
Thank you. I was just curious. I don't know why I couldn't think of when the next test was. I was trying to see if it's in
Well,
near
I
or
mean,
far.
let's worry about wood, and then we'll worry about because what I like to do is at the end of the semester, I like to give you guys choices. You understand? So
Okay.
see, so the more what I call front end load the semester. In other words, the more I cover at the beginning of the semester and all that, that all pays off at the end of the semester. Mind you, I get criticized by my department for doing that, but that's another issue. You understand? So, but
Sir,
Well, I very much appreciate it. I'm not sure how other people feel.
I know you guys do, but you know, I get criticized by my department for doing it. But anyways, that's
we appreciate it, sir. Appreciate it.
so. Look, let's worry about wood, and that's why, I like to have that flexibility. If you guys have too many exams one week, well, we just postpone it. We'll do the week after when you have no exams. Okay, but it seems that next week will be a good time. Now, I can do two things. I can I can send you the solution to assignment number 6 so you guys can verify it, or we can review the solution to assignment number 6 before the test. What do you prefer?
Can you?
Review in case there's any questions or something that it's not clear.
I prefer reviewing it right before the test. You understand? But
Yeah.
if, you know, is that okay with everybody?
Okay. Yeah.
Okay, so guys, do like I said, guys. I'm not even sure. Like, what did we cover that we didn't talk about on test number 1? I know we're gonna have, guys. You're gonna have a typical exterior wall. In other words, you're gonna have calculate the exterior wall plates. I'm sorry, studs, lintels, just like we did today. So that's gonna, and I think that's the only thing I test you on. I'm not even sure.
Isn't it from the built-up column and?
Oh yeah. Okay, so you're gonna have. Let me. If you bear with me, I'll. Well, hold on a second. Let me see what the. Yeah, exactly. So that's something I haven't covered in the last test, right? The built-up column.
No. I mean, we can skip it if you want. We don't mind.
No, but you see, the reason why I don't give you a built-up column because now you're doing one for the exterior wall. You understand? Okay, so guys, test number 2 will just be last week's assignment and this week's assignment. Just concentrate on that, okay? In other words,
Okay.
it's going to be one question where I'm going to give you a typical cross section where I'm going to show you the span of the truss and the spans of the built up columns and all that. So it's just going to be what we cover, because the reason why I don't do built up columns, because you guys are doing now for an exterior wall. If you can do it for an exterior wall, you can easily do it for the inside, which is very, very simple, right? PF, and then make sure your PR is greater than your PF, okay? Okay, so so that's all you have to worry about for the exam. Last week's assignments and this week's assignment. Sounds good? Okay. And I think that's it for this. Now, how are we doing time-wise, guys? I
It's
I have until
4:15.
Oh, we have lots of time, guys. Look, my wife's only going to come. She's only going to be calling me around to go and meet her around 7 o'clock. So we're good. I'm just kidding. I know you guys don't want to stick around that long, right?
Yeah.
Yeah, I know. Okay, so that's it. We're going to call this. If there are any questions before I close this lecture? I'm definitely going to be sending. I'm going to be sending you this. And like I said, hold on a second. I'm going to do that right now because it's pretty embarrassing that.
So can we go home now, sir?
No, we're going to talk about the lab.
Oh, we can't go home. Okay.
You are at home. I'm at home. We're all at home. What are you talking about? Omar, come on. Where were those two typos, guys, that I wanted to correct? Do you guys remember?
The 2.1.
Yeah, but right here, right?
And there's the L for the snow.
Yeah, but there was two places where I put
another one. Yeah.
On the next slide.
Exactly. No, yeah, here.
No,
The
not here.
WF 2.1. It's the on top. Go top. Yeah, here. No, not this one. Not this one. The one afterward.
But isn't this tributary width?
Wait. Actually, the last slide. I'm sorry. It's this. I think
2.4 plus 1.8 equals divided by 2.1.
This is for the width, but the other one we were correcting the length of the stud.
No, but this was 2.1 here. This I didn't have to correct this. This was correct. This was a tributary width.
It's right there where the snow
that was correct. I think it was
0.5.
just here that I should have put an S instead of a.
Yeah. Okay.
Yeah.
Yeah, I'm sorry. I apologize. Yeah, the 2.1 is correct. It was the this was a tributary width. It had nothing to do with the length. This was the length here. Did I change it anywhere else? No, this was the same thing. So these are both correct. I apologize. Okay, so that's corrected. I'll save it. So this way you guys will have the S instead of the L. Anyways, you should know by now load combination 3 is for snow and load combination 2 is for the occupancy load or the live load. Okay, so that's it for this one. Stop sharing. And let me just, okay. Oh boy. Okay, now guys, like we said, we have time. Let's, okay, share. Now, guys, it's not going to be a very long lab. Trust me. I just want to make sure we're all on the same page here. Okay, we're going to. Okay. Yes.
Do we have? Maybe you said this before and I missed it. Do we have like templates for the wood as well? Like, do we need to do some drawings for the wood project as we are doing for the steel?
Well, I gave you all that way back when. I think it was lab number. I gave you the AutoCAD template for the wood, and I gave you all the PDF examples for the wood. So I'm trying to I know I gave it to you already.
Yeah, we have it, sir.
Yeah, because I remember like when we did the when I reviewed the wood drawings, because you guys were ready to start doing some wood drawings, because we had and I believe I already gave you the template for the wood, if I'm not mistaken. So
I completely missed that.
Am I correct, guys, or is she right? I don't know.
Yeah, you're correct, sir. It's only yeah.
Okay, and like what you do is you simply copy, and you do all 4 on the same drawing, you understand? Because they're all gonna, and then when you're gonna get to the very last drawing, I'm gonna show you how you can do it at that scale, and you're going to create your own dimension variables, and you'll be able to, I'll show you how to do that when we get there. You understand?
Right.
Unless you guys like to doing viewports and all that. I don't bother with that. Okay, so guys, we'll talk about the lintels and exterior columns, and now we'll be able to relate to it to a floor plan. Okay, so if you remember, this was our floor plan. Okay, now what I did here, now guys, I don't know if you noticed this, but this drawing is approximately 1/8 of an inch is equal to 1 foot 0 inches. Has anybody tried that? In other words, if you take your scale, your imperial scale of 1/8 of an inch is equal to, just check here if you printed this out, if you have 42 feet. Anyways, I think that that's what the scale of this drawing is at approximately, okay? Now, what I did here is so that we don't have guessing games, okay? When I put here L1, 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 even though they're not exactly, I want you to design this for a span of 1.83 meters, okay? So L1, 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 even though this is not the same length here, you'll assume that it has a span of at least 1.83 meters. This one here, even the one in the bathroom here, okay, and this one here, you will assume that they're all 1.83 meters. So see if you can get away with a 2-ply or you need a 3-ply there, okay? Now here you have very little because the loads are going this way, but don't worry about that. Now, the biggest one, the one that we did right now in the lecture would be this situation here, okay? Now, this is not a column here, guys. That's a mullion for a window. And this is not a column. That's just a door frame. So when you look at it from this point of view, okay, this is exactly the same view that we had in our assignments, okay? Where if I look at that view, I have a big window here, I have a column, and then I have an opening for a door, and that's what you see in between here. I'll do a different color. This here is the door frame, and this is the mullion of the window. So that's not another column. So therefore, the lintel would go like this. So therefore here, when I'm saying that L3 is 9 feet, okay, this is the length of this one here. I'm sorry, L2 is 7 feet. So take this to be 7 feet here, and take that to be 7 feet there, okay? Which would give you 2.13 meters. And that's what you use to calculate the lintels and the column over here. Now, so you're gonna first calculate your columns, lintel 1, lintel 2, and lintel 3. And then once you've, or you can calculate your lintels and your columns at the same time. Now remember, whatever column you need for this lintel here, it would be the same column there, the same column there, the same column there, the same column there. You understand? So this is where the columns would go. So that's all you need to know. So I want everybody to write down this information or take take a screenshot of this. Okay. So for lintel number 1, or I can send you just send you the whatchamacallit, the whole PowerPoint. It's up to you guys, whatever you want. I don't care. But so here, what I'm asking you to do is see if all of a sudden lintel number 3 here, because it's 9 feet, what would be the size of this? Okay, of course, since this is longer. But all these other ones here, even though this is it's not exactly 6 feet, it would maybe be 5 feet. You don't care. You would design this lintel here, and you would put the same lintel here. Even for this window here, it's slightly smaller. So whatever I design here, I'm going to put it there. And of course, this becomes the... and of course, this is 7 feet here as opposed to 6 feet. So therefore, the span is a little bit higher. But then this column here is slightly different because it carries the load from here and from here. And therefore, this column would be totally different. Okay. And remember, whatever column you get here, okay, you don't necessarily repeat it there. Okay. Because this column here would be it would only carry that much load. Okay. And this column here would only carry that much load. So whatever column you get in here, don't put that there and don't put that there. It doesn't make sense, okay? Most likely, whatever column you have here. Now, here on this side here, okay, if you want to know, like, for example, the tributary width for the wind load on the column, well, what you do is this. This is my opening right here. Here's my lintel sitting on top, right? And for example, worst case scenario is what? Okay, so this is a span of 1. Where would be the furthest stud away from this opening here? Where would the furthest stud ever be?
600 meters.
Exactly, like 0.6 meters, okay? So therefore, the tributary width for the wind load on this column would be that, up to 6.6, and that would be the maximum, you understand? So you go half the span here, and then and then you go up to 0.6 meters here. So in other words, I would take, for L1, I would take this plus 0.6 meters divided by 2, and that would be the tributary width of the wind load acting on that column. I hope everybody can appreciate that. So this is the these are the dimensions I want you guys to use. I did this purposely because, you know, if you're going to use a graphic scale, you're all going to end up with different values. This for me is good enough, okay, for all practical purposes, okay. And therefore I want you to use 6 feet for lintel number 1, 7 feet for lintel number 2, and 9 feet for lintel number 3. And lintel number 3 is only here, lintel 2 is here, and the rest you consider them to be lintel number 1.
Sir?
Yes.
Well, lintel number 1 on the right bottom corner is very small.
I know, but whatever I'm going to, if the span is smaller, if it's good for a 6-foot span, will it be good for a 5-foot span?
Yeah, sure. Okay.
See, you follow what I'm saying? So you're trying to be practical, you understand?
Yeah.
So in other words, if I know that this lintel here is good for a 6-foot span and this one is only a 4-foot span, is it going to work there also? Definitely.
Okay, so that would be easier for us because we can just...
Exactly. In other words, you could just, like when you would specify in your drawing, you would specify, for example, you can either have a table here, okay? And you can have, you know, L1 and you can specify what you're using. And then here you can put C1 and then you can specify what C1 is. You understand? It's up to you. You can either put it right here on the drawing or you can have like a schedule of how you want to show the members for the, you know, it's up to you. Okay. So for example, here, like when I'm doing my drawing, the best thing to do is like, you don't draw a built-up column in your drawing. You simply draw, like you draw a box and you draw an X across it. That shows that it's a column. And then you can either call it, you know, you can call it C1 and you can have a schedule. C1 is 3 2x6s, whatever, or you can specify right here on the drawing what these are. Okay. And you can't put typical because they won't be typical all around. Okay. So it's up to you. When we get to the drawings, I'll show you different options you have to annotate how these columns are going to be on your plan view for the ground floor. And the same thing here, you can actually put L1, L1, L2, L2, and then you can have a legend here saying L1, okay, 338 by whatever or whatever, you understand? And you can have a schedule showing what these lintels are, or you can actually put them right on the drawing. It's up to you, okay? So that's for the lintels. Does anybody have any questions? Is it clear what we're going to need to do? So that, and I don't know what I have on this sheet. Oh yeah, so basically here, okay, this is just to show you, for example, what are your tributary widths, okay? So regardless of whether the lintel's in the front or in the back, okay? Oh, sorry, I don't want that. So regardless whether the lintel is here in the back of the house or at the front, as far as the tributary width going in one direction here, they're all the same, okay? So that's the tributary width that is being supported by that lintel, and that's exactly the same tributary width that's being supported by that window, okay? So that's what you have to keep in mind. And what else do I have? So here for lintel number 1, the tributary width would be, for example, here you notice what I did is I took the maximum spacing of 24 inches, okay? Half of lintel 1, that would be the maximum spacing. I should have divided this by, for lintel number 2 and for lintel number 3. So I'm even going to give you the 183 divided by 2 plus 0.6. I should divide this by 2 also. I made a mistake here, so I apologize. So this is 1.83, okay, plus 0.61. Don't take this divided by 2. That would be for the wind load, you understand? In other words, when you're calculating the wind load for the built-up column that's going to be supporting a lintel, you take half this and half that. So this is wrong. This is 183 plus 62 divided by 2. So I apologize for that. What did I put 6.61 here? What did I do here? Anyways, these are all typos. I apologize for that. I should have checked these. So if we go back, I'm going to go back. Oh yeah, sorry. So the dead load is what we used previously. The snow load is what we had calculated previously. The tributary width here in this direction is 4.69 meters. Okay, and then the tributary width for the columns. Like I said, this is, let's go back so that we can see this properly. Okay, L1, L2, L3. So let's go back. So like I said, we're going to correct this right now together. So let's go back. So for L1, okay, if we look at here, we know that the wind load, half the wind load is going to go here. So in other words, it would be half the span here. We all agree. And the furthest stud would ever be from that window would be at 0.6 meters here, or 0.61 because I put it at 24 inches. And therefore the tributary width for that column would be L1, 1.83 plus 0.61 divided by 2. So we're going to go correct it on the other page. We'll put the right value. And of course, the same thing would apply here. Okay, so this would be 2.13 plus 0.61 divided by 2, and that would be for L2, in other words, for this one here. Oh, wait a second. That's for this column here, okay? For this column here, of course, this would be the tributary width for that column there. Okay, so in other words, it would be 2.13. For this column here, it would be it would be pretty redundant, 2.13 plus 2.13 divided by 2. So in other words, for this column here, the tributary width would be 2.13 meters, okay, for that one there. And for number 3, of course, the same thing. If this is a span here of 2.74, and then the furthest stud here would be at 0.6. So let's go back and correct all of those on the other page. So this way, when I send you this, you'll have all the right information. So let's go back here. So L1, let me just escape, and I'm going to correct this. And show. Okay, so let's go back here. Like, I apologize. This should be. Can somebody do the math so I can put the right value, please?
It's 1.22, sir.
The same, yeah.
I'm sorry, what'd you get?
1.22.
1.22, you said?
Yes, sir.
Thank you. So that's going to be the tributary width for 1.22. For L2, well, that's only for the column in the center. Okay, we agree? You understand? And then for this one here, it would be do the same correction here. This was a 0. Boy, was I tired when I did this. I don't know what I was thinking. So, and then of course, divided by 2. And would somebody give me the answer here?
So 1.68.
1.68.
Yeah.
68. And now, if you want to calculate the end columns, for the ones that are supporting L2, it would be for this is for the end column, not the one at in the middle of the 2 lintels, you know, for the end columns for L2, the end column, okay, L2 end, I'm going to put end columns so that we know what we're talking about, end columns, or end, not the end columns. Well, we're going to say that's equal to the same thing here, 2.13 meters plus 0.61 meters divided by 2, and that's equal to
1.37, sir.
1.37. Thank you. Okay, so and I apologize for these little mistakes. I mean, okay, so there, now you got all the information. I'm going to save this and I'm going to send you this PowerPoint so you'll have the right information, so you'll be able to, okay? And keep in mind, like this is going to be the height of your column, whatever size the lintel. You can actually remove the height of the lintel if you want to, when you calculate the length of your column. It's up to you. If you don't, just leave it as 2.44 meters. It would be, you know, still correct. And that's it. So once you've done that, I believe we're getting to the end almost of what we need to design for this project. You know, once you design this, that's it. I think the last thing you need to do is just design the gusset plates for your trusses, and the design is complete for the wood. I think so. I'm not sure. How does that sound? So does anybody have any questions?
I do have a question about the truss.
Okay, so let's go back to the truss. Can you share your screen? Oh wait, before you ask the question, Anton, are you there?
Yes, sir.
Yeah. Did you get my email, Anton?
Yeah, I got it, but I figured it out.
Okay, because like the question you asked me, Anton,
yeah, I know
it
it's
was
so vague.
so broad. Yeah. Like I said, where do I start? Okay, so you don't need me to address that. Okay, I just wanted to make sure of that. Okay.
Oh, thank you, sir.
You're welcome. So Rena, go ahead. Like, you want to share your screen with us, or do you?
No, I don't want to share my screen because I don't have a question on the screen. I have it on my notes. I just had some questions that I wrote down.
Okay, so let me just put on the white screen, and this way we can maybe use a right screen to describe whatever we want.
Actually, I can show you my ADA, and then this way I can ask you which one.
Okay, go ahead.
Let me see. Okay, yeah. So this one, can you see my ADA?
Yeah, go ahead. Like, you want to show me your ADA? I'm going to stop sharing this. You want to show me your ADA? Great. Okay.
Yeah. Okay. So because you said, I think that's what you said the other students sent you in the design brief. You said that you had to calculate like the compression and the tension of the columns. So I was wondering if we had to do that. So like it would be like this one, right? Or like this.
Okay. So let's okay, hold on. Can I ask request remote? I'm going to request. Okay.
Okay. Yeah.
Okay. So can we clear what you've done so far? Let's clear
that.
Okay. Now, I want to, did you give me authority to okay, so I'm okay. Now, right now, Rena, this here, if you look at your ADA result, you have a negative value, okay? Do you understand?
Mm-hmm.
A negative value means that this little member here is in compression.
Yeah.
Okay, so that means that now, if you look at this member here in compression, unfortunately, there's no sheeting, there's no nothing, okay? So what you're gonna have to do is you're gonna have to calculate P, like for example, how come I can't write, okay, PR, okay? You're gonna have to use the equation, okay? And check the PR for a length of 2.7 meters to see if it's greater than the value that you have from ADA. And I'm sure it's gonna be, but that's what I wanna see.
What equation? I just don't remember. Like
PR is equal to phi.
Or like in what lecture do we see that is just for the studs, like a stud?
Like when we were doing compression members, like
okay.
for the studs, exactly. Yeah. You remember, like if we can't go, if for example, remember as soon as we answered one of the questions in the checklist, we couldn't use the table anymore. We had to do it with the equation.
Mm-hmm.
Okay, so you're going to use that equation. Okay, this is the equation: phi f c. I'm trying to remember. Oh, a k z. It depends which one's going to govern. In this case here, the PRB is going to govern. Okay, because you understand, it's the PRB that's going to govern. K, so this is KZB and KC. Remember that equation?
Yeah.
So therefore, like this you get from table 3.1, This you calculate from table 3.2. A is what? A is 38 by 89 in a sense. And you just show that for a 2x4. And then if you want, remember that here you have studs, like I think the table is for, you have at least 3 members side by side. Therefore, you can take the values directly from the table for this here, okay? And you just take standard dry condition for the phi FC and you calculate the PRB. And you know, you start off by showing that the that the slenderness of the B governs, okay? Remember like how to calculate C is equal to K L D over D. And what's D? Well, D is 89, right? This is okay. And then it's or KC is equal to KLB over B. And of course, this is the one that's going to govern because it's going to give you a higher slenderness ratio. And then you just calculate everything based on the C for the B, understand? And here, and this is the length of your column, 1.27 meters.
Okay, and then for the other one, for the
No, that's just
same
for that one. Now, this one here
Okay.
is intention, okay?
Mm.
So intention is very simple. You go to the table, you see the TR value for a 38 by 89 is equal to, for example, I think it's about 25 kilonewtons. You understand?
Mhm.
And you can even multiply the values in the table by 1.1 because you have a case 1 system. So you can actually increase them by 10% and just show that it's greater than your TF value that you have for this member here. And I believe the TF value here is about 5 or 6 or 7. I don't remember.
Okay.
Is that okay?
Yeah.
Now, so that's for those 2 members. Now, for this member here, okay, you have to use PF over PR squared. You understand? You have to use the interaction equation, okay, plus MF over MR times, you know, like the whole 1 over, you know,
Why
that
is
whole,
the one like different? Wouldn't the one from the right will be the same as the one from the left?
you mean this member here and this member here?
No, because are you talking about the one that's 1.27?
No, I'm talking about now the top chord.
Oh, okay, the top chord. Okay.
See, because the top chord, what happens in the top chord, okay, is that you have an axial force in the top chord, which is in compression.
Okay, yeah. Yeah.
And on top of that, you have these bending moments. So therefore, you got to take the bending moment here and the axial force there. So this becomes your MF value. This becomes your your PF value. Now, the PR is very simple. You simply, then you have sheeting laterally supported, so it's as if you're designing a stud wall. You go get the value in the stud wall, okay? And the MR is very easy. You simply go to the joist selection table and find out what the MR is for case 2, and that's where you get your PR and your MR values.
Okay, for that one, I was wondering, I used the unsupported length that it was 1.27, but I don't know if that's the one I'm supposed
This
to.
one here, for this one here, yeah, your unsupported
No,
length.
for the top chord, like
No,
because
the top chord, the unsupported length is 2.36 meters, assuming that you
okay.
join. You see?
I wasn't sure like what the unsupported length was.
The only thing you can do here, if you want to make it a little bit more interesting, because here it's continuous, okay? Like it's pinned there and continuous there, you can take a K value, if you want, you can take a K value of 0.8 instead of 1.0. You know, when you do the K, the KL over whatever, understand? If you can use 0, but if you use 1, it's even better. Okay, so that's for this one. And then for the bottom chord here, the equation you use, okay, you use TF over TR. The TR you get from the table. The same TR that you had for this member here is the same TR for that member there, okay? And this one is very simple, plus the MF that you get here from ADA divided by the MR, okay? But don't forget, now the MR, you go to the joist tables for this one, you take a single member, the MR for a single member and you multiply it by 1.1 because you have a case one system, because you have you're going to have at least 3 trusses, not spaced, you understand, and so on. So for the MR for this, you take it from the joist tables, but you use single member and you multiply by 1.1 because you have a case one system. You don't have a case two system because you don't have the sheeting on this one, understand? For the MR value. And that's it. So once you've done that, if all the values turn out to be, like for example, if this ends up being less than 1, I'm okay for a 2x4 here. If this ends up being less than 1, I'm okay with a 2x6 there. And of course, if these end up being correct, they should be correct. Like I said, normally these members here are made with 2x3s. And I'm going to expect you to calculate everything manually with a 2x3. So I said use a 2x4. Because normally these web members 2x3s would be sufficient. So I know that 2x4 should be more than adequate, but I want you to do the calculations anyways.
Okay, and I also had a question for the deflection.
Oh, the deflection. Okay, can we clear all this so that we don't?
Yeah, am I supposed to do it, or can you do it?
You do it. Just clear it for me if you don't mind. Okay, now for the deflection, what you do is once you're satisfied that this could be a 2x6, once you're satisfied that this can be a 2x4, once you're satisfied that this can be 2x4s, you understand? Once you're satisfied, excuse me, what happened was is that like what you do is simply in ADA, okay, in ADA you take load combination, okay, you call it, I like to call it serviceability limit states in ADA. Do a load combination called serviceability limit states, okay? And that's what you're going to call this combination, because to design this, you call this one ultimate limit states, the first one for the forces. And then when you go to your load factors, all you got to do is like when you pick your loads, okay? You only pick your snow load here. Just take the snow load all by itself, the snow load, and use a factor of 1.0. That's what serviceability is. You don't factor your loads. And then you run the analysis, right? You run the analysis and you look at ADA, see what would do the deflection under that snow load. And that's all. And if it's less than L over 360, then you're okay. And
yeah, but what I mean is like, what is L? Is it like
the L,
or like
okay,
the whole thing?
Rena, what is the definition of L in your mind? Huh?
Like the length of the stud, like whatever work.
No. It's got nothing to do with length of stud. What is the definition of L? What does L stand for?
Well, I don't know then.
L stands for span.
Okay.
Right? That's what L stands for, the span. What in your words, tell me what the span is.
In my words, is length, like an equivalent of length.
No, don't worry, Rena. Tell me in your own words. Don't worry if you don't. Just tell me in your own words what is span.
Well, like whatever's
span. Like if you want to have the textbook definition of span, is that it's halfway through the supporting member here, halfway through the supporting member here, okay? And the distance between halfway of that supporting member to this supporting member, this is the span. That's L.
Okay.
As opposed to LN. Remember last year we talked about LN, which is the inside face of the support to the inside face of the support. But that's only for concrete you do that. For steel and for wood, we always talk about spans. So in other words, here we're assuming that the walls are at such a distance, you understand? And therefore we take that to be the span.
Okay.
So L would be, I think it's 27 feet 9 inches. Okay. So Rena, do this on your calculator right now. Take 27.75 on your calculator.
Okay.
Multiply it by 0.3048.
0.3. Okay.
048. You got that?
Multiply it?
Multiply 27.75 on your calculator by 0.3048.
Okay.
What do you have?
84,582.
What? 84,000?
Well, you said multiply 27.75 times 0.2.
27 27.75 multiplied by 0.3048. On my calculator, I end up with 8.4582.
I don't know what I did wrong then.
Then if I multiply that by 1,000, that gives it to me in millimeters. And if I divide it by 360, so the maximum deflection I can have here is about 23. The maximum deflection I can have here is 23.5 millimeters. So if the deflection here in ADA is less than 23.5, that means it's stiff enough.
Deflection there on that member?
Well, wherever the biggest deflection is, because this is where the drywall is going to be, right?
Okay, so if the deflection there is less than
In other
that,
words, you just look, once you do this load combination here, okay, once you do this load combination here, what you do is this, okay, very simple, okay, you as a matter of fact, can you run?
yeah, I was gonna ask
Okay,
you.
let's do it right now. So let's do it right now. Let's go to load combination.
Okay, I think you have. Okay, I'll do it.
Yeah, you do it because it's much easier because you have better control. Go to loads. No, don't analyze. I want you to make sure that don't analyze yet. I want to see. Go to loads. Here, load.
So it got this one.
Yeah, what is that one? Is that, did you already create one?
Yeah, I did.
You did. Okay, so okay, so there. So that's your snow load. Perfect. And now, can I just go here? Go to load here. I want to go to load combination. I want to make sure that you have the right load combination. Okay, so you do have it, right?
Yeah.
That's perfect. So you have it. Okay, so in other words, okay, so no, okay, that's it. Okay. Now run your analysis. Oh man, this is super fast. It's amazing. Then you do this one here. Okay, and then look, if I come here, I take this, okay, and I double click on this one. That's the displacement, 8.86. That's the deflection right there. And you can.
Okay, I thought it was talking about like the member, not the.
No, that's the deflection. In other words, that's the one. Understand? Now, if you want to see it graphically, then of course you come here. Okay, you go to results, but that's how I do it. You understand? There, you have it there. Okay, apply. Okay, you have exactly the same value, 8.86. There's your deflection, and you're allowed to go up to 23.5. So that means that you're way under L over 360. So what I like to do is I like to come here, I like to double click on that node, and I see the value right away. You see?
Okay.
Is that simple enough?
Yeah, I guess I just got confused with all the terms and everything.
Look, Rena, don't be afraid that it's very confusing for all of us at the beginning, okay? It doesn't look confusing to me. Why? Because I've been doing ADA for 15 years. You understand? I've been doing, so like it's a little easier for me to be, but don't be ashamed. We all get confused, okay? And it's good that you clarify these little confusions because then you're not going to be totally lost. You understand? I'm pretty sure that now, because we're doing this project with ADA, right? That you have a better appreciation of what ADA can do for you than when you did it the first time. Do you agree?
Yeah, for sure.
That's it. So that's what's important. You understand? So you're starting to realize the benefit of the program versus doing everything manually, that you can let the program do a lot of the busy work and you get the information you need in order to do your design. That's what I want you guys to get out of this whole thing. You understand? So
okay.
You're on the right track. There you go. Okay.
I'll stop sharing now.
Sorry, yeah, stop sharing. So guys, for those of you that had the same issues, I hope that clarifies it. And please don't feel shy. I mean, we're all here to learn, and don't feel shy to hesitate to clarify any glitches. And I will definitely, I don't think there's any stupid questions. I've always said there's only stupid teachers that don't know how to answer them. So just worry about that. So are there any more questions before we call it a day? So what I'm going to do then, if there's no more questions, because yeah, Nermin, you have a question? Does anybody
No,
else?
sir. No, I was saying thank you.
Okay, so guys, like, do yourself a favor. Do assignment number 6, because that's going to be the bulk of your test number 2. Do that assignment, okay? If for whatever reason you can't seem to get it, okay, and at the same time you should be able to get it, just follow. I'm gonna send you, of course, I'm gonna send you the video link. I'm gonna send you the lecture. I'm also gonna send you the lab, okay? So I'm gonna send you that. I'm gonna send you all 3 this week. And please do the assignment earnestly. That's really going to prepare you for the, like I would, you know, I would review, I would try to do the example we did in class, totally, you know, just take the information, see if I can solve the problem. And if I can do that, do the assignment. And next week, when we review the solution to the assignment, if you guys have it bang on, you should have absolutely no problems doing the test. So, and so far, guys, you've been doing great. I appreciate the effort and the results I've been seeing. So thank you for that. And if there's anything else, we can call it a day, or we can stay here and chat about the
Sir,
year. Yes.
when we do the when we continue on the project, we just do what we did in the class today, right? Because we're designing for the build-up column and the lintel.
Exactly. And that, and all I'm trying to show you now is how do you relate it to a floor plan? You understand?
Yeah. Yeah.
So you understand? So this way, when you're looking at a floor plan, you don't get intimidated. What do I do from here? You understand? Like I'm trying to show you that everything that we're doing academically from a textbook, see, in a textbook, they just give you like values. This is your load, this is your tributary width, this is your span, this is this, but where does it come from? I want you to be able to relate to that in an actual drawing. And that's what I'm trying to, that's what the project is supposed to do. So that when you do it the first time from an actual drawing, you say, well, where do I start? You follow?
Okay, makes sense.
Makes sense, right?
Yeah. Well, thank you.
Oh, you're welcome. You're welcome. I mean, whatever I can do, guys, whatever I can do to clarify it, make it easier, just let me know. I'll try my best, you know.
Sir, I also have a quick question.
Go ahead, Gordon.
Because I remember in the video, you showed our specific dead loads from ADA and then the snow load. Those are in kilonewtons straight away, right?
I'm sorry. The dead load, I think I gave it, if I'm talking about dead loads, I usually give it to you in KPA. Yeah.
In KPA or kilonewtons? Because I was kind of confused.
Well, it depends. If we're talking about loads, I usually give it to you in KPA. If we're talking about loads. It depends. Like, in other words, is it a force? Then I'll give it to you in newtons. But if it's a surface area that has a certain weight, then I give it to you in KPA. Okay. I'm trying to understand what you're asking me, Gordon. Like, in other words,
because when we're designing the exterior wall,
yes,
I did the calculations and then I ended up using a 38 by 140.
Perfect. That's what you're supposed to end up getting. You're good.
Yeah. The only thing is that I was comparing.
Oh, okay. Well, look, Gordon, like don't confuse the load with what. Okay, so are you telling me? Okay, let me just clarify one thing. Okay, let me just make sure that we're on the same page here. Okay. Okay, so basically, Gordon, when you're telling me the loads, I think I gave you all the loads in KPA, if I'm not mistaken. Am I correct? I think I gave you the dead load of the roof in KPA. I gave you the snow load in KPA. I gave you the weight of the wall in KPA. Remember? I think.
Yeah, and then you changed it to kilonewtons, right?
Well, I have to because don't forget, now what you're doing is that you're taking these loads here, right? Like you're taking all these loads here. In other words, you're taking all these loads that are all around this member here. Do you understand what I'm saying? And on the member itself, basically, right? And what you want to do is you want to take all these pressures and you want to see, well, how do those pressures get converted to one axial load that goes right through the member?
Okay.
So this becomes kilonewtons, okay? So how do I go from kilonewtons per meter squared to kilonewtons? Well, I take the tributary area that this member carries, and it gives me the kilonewtons here. And then what I did here for the weight of the wall itself, okay? I just multiplied this by the height, multiplied by the tributary width of each stud, and that's how I got the weight of the wall acting on the stud. So the axial load in the member is a force. It's in kilonewtons. So in other words, like, let me just clear this, okay? So basically, in plan view, okay, here's my wall. Okay, here's my other wall in plan view. Do you understand? In theory, here's my truss going from one end to the other. Do you understand?
Yeah.
Okay, so I'll put an apex there, and here's my other truss going from one. You understand? So what you're trying to do all the time, okay? Now all of these here, for example, and then I have like on top of this, I know I should be doing it this way, but on top of this, like in elevation, on top of this, I have snow load coming down, right? I have the dead load of the truss itself, of everything else. So I have all these loads here. Okay, so here my snow load is 2.5 kPa. You understand? So that in theory, what's happening is that every square meter here has 2.5 kilonewtons of force acting on that surface area. That's what a kPa is. Okay. Now, what I want to do is I want to take these 2.5 kPas here, okay, and see how much is that going to come into this one particular stud. So what I'm doing is I'm saying, okay, if I can calculate the tributary width of this stud here in this direction, right? And if I can calculate the tributary width in this direction, well, this is the area that my stud is actually carrying. Do you follow?
Yeah, I get it now.
So now if I take a pressure of 2.5 kilonewtons per meter squared, and I say so, and if I know this stud is carrying, for example, 10 meters squared, right? So therefore I can say that there's going to be 25 kilonewtons of snow going right through that stud. Do you understand?
Yeah, I get it.
And that's what you have to actually design for. In other words, what is the actual force that is going through the stud, so that you can make sure that the stud, depending on how it's, like here you have your sheeting and all that, that the stud can withstand that force without breaking, And then of course the exterior stud, what happens is that the exterior stud, you don't only have to worry about that force there, but what's going to happen is on the exterior stud, you also have this wind load that's acting on it, okay? You understand, Gordon? Okay, so what's
Yeah, I
happening,
understand.
so now what's happening is that, so what does a moment do to a member? Okay, it puts it puts compression on one side and it puts tension on the other side. Do you see that?
Yeah, I do.
Okay, now what does the axial load do to a member? It puts compression and compression. Okay, so what you're actually worrying about is you're making sure that the compression caused by this load and the compression caused by this load, okay, is less than the compression resistance that the member can carry. And that's why you have that interaction equation. That's why you have PF over PR, okay, PF over PR. Well, that's for this one here, that's for this compression here. And that MF over MR, well, that's for that compression there. That's what you're actually calculating.
Okay.
And you're making sure that the resistance of this and this ratio here and that ratio there, when they're both combined, you don't exceed the actual resistance and compression right at that point there, because that's where they both combine and they kind of overlap to cause the total stress on the member.
Okay, I get it now. Thank you, sir.
You see that? Okay, so that's what we mean by, a combined load effects. Because in the way they show you, if ever you look in the textbook, this one here, they're going to show it to you like this. In other words, this is a compression force here, okay, on the member, okay? That's what they're going to show you here, okay? Or I should understand. And that's going to, and then when they show for the bending moment, they show you always this one. They always show you that it goes from tension to compression, okay? So they show you the tension here, and they show you the compression here, and that's what they show you. And therefore, what you end up is something like this. So in other words, here the tension here reduces the compression from that force, so it's a little bit smaller, but here they add up, and you want to make sure that the total resistance here does not exceed the compression resistance of the member. And that's how you're going to see it in the textbook. Some people have a difficulty seeing it that way, understand? But those are the actual stresses that are, this is caused by the axial load, and this is caused by the bending moment, understand? And that's how the textbooks tend to show it. But you have to understand is that compression here, well, those two add up. That's all you have to remember. And that's what this does. Compression here divided by the resistance there, compression caused by the bending divided by the resistance there, as long as these two ratios, because look, Gordon, design objective, right?
Yeah.
MR greater than or equal to MF, right?
Yeah.
So what's MR divided by MR? Greater than or equal to MF divided by MR. In other words, here you get like a 1, right? So what they're saying is that the ratio of MF over MR should never exceed 1. That's the maximum value you can have, okay? So if I take this ratio here and I add a ratio, what is PR, I'm sorry, PF over PR, or I should wrote it the other way. PR should be greater than or equal to PF. Agreed? Okay. So therefore, if I take this ratio, PR over PR, then this shouldn't exceed 1. So if I have this one combined with this one, both the PF over the PR plus the MF over the MR, well, both of them combined then should be less than 1. That's what you're doing. That's simple. You understand?
Yeah, I get it now.
Okay.
Thank you, sir.
I'm glad it's a little clearer. Okay.
Sir, I have a question about the project itself.
Go ahead.
So I know we have 3 different lintels, so we have to do 3 times the WF, WS, and MF, and for each one of them, right?
Well, yeah. The only thing that you don't have to do, you don't have to calculate what your factor load is.
It's the same one for all of them, obviously.
Exactly, and then you don't have to calculate the wind load. Understand? Whatever wind load you get for case number 3, it's applicable for all 3 situations.
Yeah.
I mean, the wind load doesn't change. Understand?
Yeah.
And the wind load, we did that last week, right? We had, when we did the exterior wall, we had calculated what the wind load was, right?
Yes, we did.
Okay, so you should be able to get that information from the last week's lab. In other words, when we did the exterior wall, we went through the whole trouble calculating what was the maximum wind load that we had, right?
Yeah, it was 9. It was.
I don't remember, but all I'm saying is that, 0.9 or something?
Yeah, 0.936 kilopascal.
Okay, so that was for strength, and just remember that for serviceability, multiply that by 0.75, right?
Yeah.
In other words, because for serviceability, your I, your importance factor for serviceability is 0.75 instead of being 1.0. Okay, so you reduce that to when you're checking serviceability. That's all.
Okay.
Okay.
Makes sense.
Okay, so I'm glad you guys are asking the questions because it kind of helps to clarify a couple of glitches.
All right.
Is there anything else before we call it a day, or you guys want to talk about the weather?
One more question. I think you might have already said this, but I have to ask again. Do we need to submit our ADA file with the design brief, or
No. Like what I want to see the results of ADA. You understand?
Okay.
The only thing I'm going to ask you to submit to me is the only other file I'm going to ask you to submit to me is all your AutoCAD file. You understand? Like you're going to have one AutoCAD file where you have your 4 drawings on it, right? Plus you're going to copy them as a PDF. But the only other file I'm going to ask for is the AutoCAD. Okay. I mean, AutoCAD, if you're using AutoCAD, if you're using Rivet, I want you to give me the Rivet file. You understand? I don't care which one you give me.
Okay. Sounds good.
Sounds good. So anyways, we'll recap that more towards the end of the semester, make sure we're all on the same page with what I expect you to submit. You understand? So, and if you're ready to submit it now, by all means. I'm just kidding. I waited to it. So I think, if I'm not sure, I'm pretty sure that we only have one more thing to design for our project, and that's going to be it.
We have the nails.
Yeah, in other words, but that's you're going to see it's not that complicated. Okay, I'm going to show you the simple way of doing it, so this way you'll have an easier time of like once you calculate the resistance of one nail, you're going to be able to use that resistance for all the different joints, and all you have to do is calculate the different nails, and I'm going to show you how to calculate the spacing very easily, and you'll be able to calculate the size of your gusset plates. Okay, so don't worry about that. I'm going to walk you through it. But I think we only have 2 more lectures. One's on nailing, and the other one's on formwork.
Yeah, that's it.
I think that's it. So we're nearing the end, guys. We're getting there, slowly but surely. You know.
So it's only 2 lectures, like for
Like
the entire course.
we're gonna have one more lecture on nails, on fasteners. Okay, so and then the only ones that we're gonna actually calculate is nails, because there's like about 8 to 12, 8 or 9 different types of fasteners. In like, I hope you guys realize that a screw is a fastener. So there are tables for screws in the handbook. There's all kinds of fasteners, but the only one that we're gonna be learning about is nailing, because that's the most common fastener when it comes to wood, right? And then after that, the very last lecture, I kind of show you how to apply all of what we learned to design formwork. To show you that it doesn't matter whether it's formwork, whether it's a structure, whether it's a shed, whatever it is, the idea is the same. It's just you have to just be able to develop your geometry, calculate your loads, do your analysis, find the resistance, and you design the formwork. So we'll do some formwork. You understand?
In that case, we will have the final exam on May 6th, if that's.
May 6th, the week after. I don't care, Omar. You understand?
For us, I mean, for us, we care kind of.
I know. Look, if we can get it done by May 6th, all the better. Because then after that, all I'm going to do is when the weeks after that, I'm going to come and I'm just going to make myself totally available for any problems that you guys might have with the projects. How does that sound?
That'll be great.
You know what I mean? So like this way, you'll have that completely out of your hair. And the only thing I'm going to do is come during the lecture time, there will be no lecture. It'll just be totally dedicated to help you with your project if you're having any issues. Does that sound good?
Yeah.
Perfect. It sounds good to everybody? Good. If you guys are happy. There's did you ever watch The Godfather?
Yeah. I watched the first season.
I think it's part 3 where it goes, you happy, me happy. He says it in Italian. Contento tu, contento io. So if you're happy, I'm happy. How's that? Sounds good?
Okay. All right.
Okay, so guys, look, it's up to you. We can stay here and do whatever you want. The time is yours, guys. I mean,
have a good weekend, sir.
Have a good weekend. Thank you, Arvel. Appreciate it. So have yourself a good. Hey, don't you have class tomorrow, Arvel?
Yeah, but I'm telling you, have a good weekend.
Oh, thank you. Well, I still have. Sometimes I have a couple of emails to answer. So guys, I appreciate the questions, and if there's anything else, by all means, feel free to send me a Mayo. Always send it through Mayo. I check both, but I tend to check Mayo first. And there was only one last one. I think I forgot who sent me the question. It was Anton. Yeah, Anton made it very broad. It was the only question I ever got that I couldn't answer by Mayo. So Anton, you really gave me a challenge there. So.
Oh, sorry, sir.
No, it's not your fault, because it's clear in your head, because you're just right. Yeah. You know what you're trying to tell me, but that's in your head. But I can't read what's in your head. You understand? Exactly. So, first of all, it would be nice for you to tell me, because I have you for 2 projects. So I don't even know if you're talking about steel or wood. So it'd be nice for you to say for the steel project. So right away, I'm know in which area, and then after that talk about a specific member, and then and then it narrows it down for me. You understand? So it sounds good, Anton. Don't worry about it.
My question was actually about what Gordon asked.
Okay, great. Okay, in other words, so see, if you would have said for the exterior wall, how come we're talking of force as opposed to KPA, and then I would understand. It would have narrowed it down for me. The way you put it says, how come the force is in kilonewton? I said, what's he talking about?
Yeah, sorry, I forgot.
No, don't be sorry, Anton. I can appreciate being on your side of the fence. Don't worry about it, because it's clear in your head what you're asking me, because you're looking at that problem right there, and you said, I'm going to ask him to give me an answer. You understand? You know what I mean?
Mm-hmm.
But when you read, if you go back and you read your own email and put yourself in my position, you can appreciate that it's very, very general what you asked me. So
yeah, that's right.
It could have been applied to anything, and I didn't know where to start. So that's why I asked you, narrow it down for me, please. Let's make it a little bit more manageable. So guys, remember, by the end of this course, if your parents want you to design the cabinet in the back of the house, you should be able to design it properly, right? And if your parents want you to design their cottage, if it's a one-story building, you should be able to design it properly. Keep that in mind.
Okay.
Sounds good?
Yes, sir.
So guys, listen, stay safe, okay? And hopefully we'll, wrap this up nice. And so you guys are looking forward to having the exam as quickly as possible. Is that it?
Yeah.
Yes.
So I have more time to do the drawings.
No, I mean, we'll have time. We'll have time. So, okay, so we'll work on that. Like I said, like, look, guys, we'll have to assume that everything goes as planned. I mean, I can get sick, so that's going to delay things. So let's just assume that if everything works out, we should go and wrap this up by week 13, maybe. Does that sound good?
Yes,
Yeah.
sir.
We're gonna do the same for both classes, wood and steel. Leave the last classes for the drawings.
I think so, if all works out. But like, I'm not promise you, Arvel, I'm not promise you anything until we get there. Because, like, for example, I can one weekend, one day I can come up and all of a sudden I got a power failure in my area. My internet goes berserk. What am I going to do?
That's true.
You see, so all I'm saying is that if there's nothing that will come and interfere with the normal schedule, either our health or like
So we come to your house. Don't worry.
Oh, you can come to my house, but then I'm gonna get fined because I don't think I'm allowed more than 3 people in my house, right?
We stay in the balcony.
In the basement.
Whereas my mom would say,
Oh, all rush to school and you know what I mean? So listen, guys, if there's no technical glitch and there's no health glitch or whatever, I think that in theory we should be able to wrap it up by week 13, and we'll leave the last 2 weeks completely just to finish up the project. You understand? But I hope you guys are working on the project as we're going along, because it's going to become overwhelming between the design brief and the drawings. You understand? I hope you guys are, whenever you can spare some time, you're moving those along. You understand? So as a matter of fact, I'd like it if you guys, like, by the time we finish week 13, you just have the drawings left to do. That would be nice, That would be really nice. That means you guys would just have to worry about getting the drawings done, or if you can have even the drawings mostly completed by then you're really ahead of the game, that? So, sounds good?
Yes, sir.
Okay, so guys, have a safe one. We'll talk to you on Monday morning. For those of you that are in my steel class, we'll talk to you on Monday, and we'll take it from there.
Thank you.
Okay,
Bye.
take care,
Thank you,
guys.
sir.
Take care. You're welcome, guys.
Bye-bye.
Have a good one. Okay.